We'll take our look at the calendar. Today is class 16. Remember I had said there were 30 classes of new material that we present, so we are officially just past the halfway point. That doesn't count test days or quest days or review days. Okay, so today we are going to work with radicals, and I want to just say that we're going to be doing more with exponents today. It doesn't seem like radicals have anything to do with exponents, but they will. We'll make that connection. And I also want to point out that today is a tough day. I don't think the material is necessarily really that much harder than anything we've done before, but that there's just a lot of it. So kind of hold on, because we're going to go through a bunch of stuff in the next little bit. So today we simplify expressions that contain radicals, and it says the rules of radicals are going to come fast and furious in this lesson. Let's go to number 1 with Savannah. Okay, let's write down the answers. What number squared gives 25? 5. Surprisingly, there's another number that when squared gives 25. -5. You guys agree? Because if you do -5 times another -5, those negatives cancel and make positive 25. Keep going, Savannah. How many square roots? 2, right? 25 had 2 different square roots, 5 and -5. Go ahead.
One of them is positive and one of them is negative.
Good. Okay, and then I'll take this part. So then that symbol right there, that radical 25 or square root of 25, means the positive one. So if you see that symbol, square root of 25, I just want you to say 5. I don't want you to say 5 or -5. The only time you bring in the positive and the negative is if I'm asking you, like in words here, find the square roots of 25. But if you see the symbol, that radical symbol, it just means the positive one. Okay, let's go to Tyler for 2. Go ahead. Next line. Okay, so I'm highlighting a couple of things here. So the thing inside the radical is called the radicand, and the number in the front, that small little number up above, is called the index of the radical, and then the symbol itself is a radical sign. Number 3, let's go to Jeremy. Okay, so this first one right here, if anybody know how to read that symbol in English? So it looks like 3 radical 64, but I don't want you to say it that way. Anybody know what is it? So without the 3, we would call it a square root of 64, but that 3 means it's no longer a square root, it's a cube root. So this is looking for the cube root of 64. That is to say, a number that when you multiply by itself 3 copies of it, it gives you 64. It's not 32. Because if it were 32, then it would mean 32 times 32 times 32. 4 is good. Everybody okay with that? Yeah, so because 4 times 4 times 4 is 64, 4 is our answer. The next one. So we have square roots, we have cube roots, and then after that we pretty much just say the numbers. So here is a 4th root of 16. So that is to say a number that when you multiply it by itself 4 copies, you get 16. Anybody know what that magic number is? It's 2. And a lot of these roots you either memorize or you look them up on a table, or you have just a miracle where you say, okay, I'm just going to try some numbers and hope that it works. And if you try this one, 2 times 2 times 2 times 2, you get 16. So that's kind of a miracle if it just sort of comes out of no place. But again, you guys have that Perfect Powers reference sheet, and so that's going to help us on problems like this. So everybody take that out if you don't have it out already. And if we're looking for the 4th root of 16, which column should we be looking in? The fourth column, all those fourth powers. And you're looking for the number 16 in that fourth powers column. And once you find the 16, you go all the way to the left. And what number do you see? 2, which is the answer to this problem. Okay. All right. Coming down here to number 4 will help us illustrate something in general that's happened up above. We know that the cube root of 64 is 4. That's what we just wrote. But 64 is the same as 4 cubed, yes? So then the cube root of 4 cubed is 4. That's the same as cube root of 64 is 4. Agree? And so if we happen to have something like, I don't know, 17th root of 35 to the 17th power, I don't happen to know what the 35 to the 17th power is, but I know what the answer to this problem is. Go ahead. It's 35. Do we buy that? Taking something and raising it to the 17th power and immediately taking the 17th root accomplishes absolutely nothing. And so we go from 35 to some monstrously big number, and then we shrink it right back down to 35. And that's exactly what's illustrated here. Cube root of 4 cubed, you don't actually need to do 4 cubed to know the answer is 4. And so in general, if we see something like cube root of x cubed, what does that equal to? It's just plain old x. So cube root and cubed cancel. They're opposites of each other. And how about a number 5? The 4th root of x to the 4th is x. So again, if you see the power matching perfectly with the index, that's the little number in the front, they cancel. And we just get the thing that's inside. Okay, in number 5, I have told you a slight lie. The answer isn't quite x. We're going to just call it x for right now, but in a few minutes, like at the end of this demo, we'll update it and tell you the full truth. Let's go to number 6. We'll go to Ramses for 6. Can you look on with Tyler there? Okay, so let's take a look. We're starting with the cube root of x to the 21st. We're now going to talk about how to simplify that expression. So I'm going to cross this thing off for a second. You don't need to cross it off, but just temporarily I'm covering this thing up. Would you guys agree that if I could somehow miraculously write this cube root of x to the 21st as the cube root of something cubed, then that's a great way to write it, because I know that cube root and cube cancel each other. And so the answer will be whatever I'm covering up here. You guys agree? So like this is a reasonable goal, is to try to write that x to the 21st as somebody cubed. Well, you guys know that when you have an expression like this, what happens to those powers? We add them, we multiply those guys. So if I'm interested in writing cubed times some power to give me 21, do you guys buy that 7 is the right power to put in there? So I still have x to the 21 inside, right? It's equal to what it was before. But then as we said, when we see cube root and cube, they just plain cancel, right? They're opposites. And so what's the answer here? Is x to the 7. Agree? Okay. So there is a little shortcut here. If we just look at the cube root of x to the 21st and recognize the answer is x to the 7th, what's the shortcut with the power in the index? Is we divide, right? 21 divided by 3 gives 7. I'm not a fan of memorizing rules. At some point, I do want you to just have this memorized. I'd really like you to understand why it worked. Why it worked is illustrated in that example. And so number 7, we'll go to Will. Nth root of x to the k. X to the k over n. You guys buy? That's just saying take the 21 and divide it by the 3, And our answer was x to the 7th in that problem. Right? So we take that guy and we divide it by this guy. Ramses? Don't say it out loud. Everybody write down your answer to number 8. 4th root of x to the 20. I just want you to write the answer. Our little shortcut we just developed says you're supposed to take that power and divide it by the index. All right, Ramses. Agree or disagree? Agree, right? Easy, easy problem as long as you know this little shortcut. Right? The difficulty here is that we've got a wealth of shortcuts that we've developed over the last 2 classes, and we're going to see even more shortcuts, formulas today. And so it's not that that's a hard rule to follow. It's just that when that is in the sea of a bunch of other problems involving other rules, it might be hard to recognize, oh, it's this particular rule. And I just want to point out one other thing. It's not written up here, but let's suppose that I give you this cube root of 64 x to the 15. So let's handle the x to the 15 part. What does that become? Everybody agrees x to the 5th, and 15 divided by 3. In the front, it is very tempting for some folks to say, okay, I'm supposed to take everything inside and divide it by the 3. That just isn't true. We took that power and divided it by 3 because that was just a regular old shortcut. But the cube root of 64 is not 64 divided by 3. What is the cube root of 64? It's 4. 4 times 4 times 4 is 64. So I just want to point out we have to treat completely differently the cube root of that plain number 64 versus the cube root of x to a power, x to the 15. Okay? So they're right next to each other, 64 and x to the 15, but the way you handle them is completely different. So it's a really specialized shortcut we just developed there. Okay, let's go to number 9. We'll go to Alex. Okay, first one says square root of 9 times 4. So let's do 9 times 4 first. How much is that? 36. And the square root of 36 is 6. And then completely separate calculation, square root of 9 times square root of 4. Square root of 9 is 3. Square root of 4 is 2. And when we multiply them, 6. And it turns out that it's no coincidence that those two things give exactly the same answer. It works all the time. Is that if you have multiplication inside of a radical, like in part A, you can separate it into 2 different radicals and multiply your answers at the end. Okay, so that's written down below. It's this thing we call the product rule for radicals. The nth root of A times B, you can separate it into 2 different radicals, nth root of A, nth root of B, and then multiply at the end. Turns out you can do exactly the same for division. We won't verify that with an example, but division works exactly the same way. Okay, so on the next page, we will see how we're going to use this. I'm going to ignore all of this stuff here. You're welcome to put a line through it. We're basically just going to build it from scratch here. But what we're going to do is simplify this expression up above. Cube root of 16 x to the 4 times cube root of 2x to the 19. Okay, so let's give this a shot. So what you could do, there are 2 options here. You could try to simplify each of those radicals separately and then maybe put them together at the end. But then you might have to simplify the final thing again anyway. And so it turns out it's more efficient to put them together first and simplify just once. So that's what we're going to do. So first thing, I see 2 radicals next to each other multiplied. I can push them together and make 1 radical, just like the property we saw a moment ago. So this is really equal to cube root of 16 x to the 4 times 2x to the 19. It's that same property that we just saw. Yes? Irene?
What happens to the other?
So the 2 cube roots merge together and become a single cube root, but it is important that those were exactly the same. They both had to be the same kind of root. Then we couldn't do anything if they weren't the same. If one's a cube root and one's a 4th root, there's nothing we can do with that. Yeah, so the property that we just saw is this guy. If you have two roots that are the same as each other multiplied together, you can smush them together and make one root. Okay, so let's clean this up inside. So shuffling things around, 16 and the 2 get merged together. That's a 32. X to the 4 times x to the 19. I can mush them together as well. What do I do with those powers? I add those ones. So 4 and 19 is 23. Okay, so here's the tricky part. Cube root of 32, is that something nice? If you don't have it in your head, you can look on that little formula sheet, right? 32 is not there. What would we do with the power 23 and the index 3? We divide them. That's the shortcut that we developed. Can you divide 23 by 3? Well, you can't get, it's not an even, right? It's not an integer. Ramses? Okay, so here's the, that's exactly what we're going to do. We're going to split that 32x to the 23 up into two different pieces, one of which is going to be a perfect cube. It's going to be really nice and we can deal with, and the other is just what's left over. So Ramses has exactly the right idea, even though he's been texting all class. But it's exactly the right idea. We got to split this thing up. Okay, so 32 is not a nice thing to have inside of a cube root. So look in your cubed column, the third column. Yeah, you want to find a cube that goes into 32. So look in that cube column, find a cube that goes into 32. What is it? It's 8. There are other numbers that go into 32. For example, 16 goes into 32. But like 16 doesn't help me inside of a cube root. So it's not just like find any old number that goes into 32. It's find a nice number, in this case a cube that goes into 32. So I'm going to rewrite that 32 as 8 times, and what's left over? 4. And the cube root of 8 is something nice, and the cube root of 4 will just be in our answer. Okay, and then x to the 23. This is the trickier part, and this is really a good insight that Ramses shared. 23 is not divisible by 3. So we're going to peel off one of those x's. Suppose that you had 22 of them. Would that be any good for you? 22 divided by 3? That's no good either. So peel off another x. 21 left over. Is 21 divisible by 3? Yes, so that's our winner. So we're going to take 21 of those 23 x's and we're going to put them in the good radical. And then the other x's left over get shoved back here. How many? 2. You guys believe we still have 23 x's? Haven't cheated. All we've done is break them up in a good way. And then I think we're good because the cube root of 8 we can handle. What's the cube root of 8? 2. Cube root of x to the 21. Now we do our division shortcut and get x to the 7. The cube root of 4 is nothing nice, so I'm just going to copy it. Cube root of x squared is also nothing nice because 2 is not divisible by 3, and we're done. So this is what we mean by simplifying a radical, is you pull everything nice out that you can, and then you leave in whatever's left over. Yeah, we factored 32, but we didn't just factor it in any old way. We factored it by looking at that perfect powers list and recognized that 8 is a nice number. And so we factored the 8 out, and then 4 was left over. Yeah. So this kind of problem, I think, is really tough until you get a little bit of practice under your belts. So there's our answer there. I'll put a little dot to highlight the multiplication. Okay, so basically what we did is written out in detail here in C. You can check it out later if you just kind of want a reminder of what we did. Let's take a look at number 12. So let's find the value of each of the following radical expressions, square root of 9 plus 4 and the square root of 9 plus 4. Okay, so the first one? 3 plus 2 is 5. How about this guy? Square root of 13. Are they equal? No. So the thing that we saw on the previous page where they were equal is special. It's a property of multiplication, and it also worked for division, but it does not work for addition, and it likewise does not work for subtraction. So tempting as it may be, if you see something like this, you might be tempted to say, oh, square root of x squared is x, square root of y squared is y, and then the plus sign in between. Right? Might be tempted to think, okay, I can just take that square root and push it all the way through and add up at the end, and we just can't do it. Doesn't work. Didn't work over there. So again, if you're not sure, like if you've got some property of radicals or exponents that you don't know, like I think I'm supposed to add these, or I think I'm supposed to divide these, but you don't know, just make up a small numerical example like this 9 and 4 one, and that will convince you whether it's legitimate or not. Right? Okay, so let's go to 13. Marcy. Not equal. Good. So angrily put some more lines in there, because like you're never ever going to write that down because it's just not true. Right? Addition and subtraction we cannot do anything with. Let's go to Kayla for 14. Okay, so part A says we're going to add these two like radicals, 5 radical 7 plus 3 radical 7. There are a few different ways that seem reasonable to do this that aren't right, and there's one way that hopefully seems reasonable and is right. The correct answer here is 8 radical 7. But other possibilities are like 8 radical 14 or 8 radical 49. You might think, okay, I'm supposed to do something with those 7s, but you aren't. And in my head, I've translated this into a 5x plus a 3x. You guys agree that it's equivalent to 5x plus 3x? And what is 5x plus 3x? It is 8x. This is something that we know very well. And you didn't do anything with that x. You just copied it. And you said, oh, I have 5 of them and then another 3 of them, so I have 8 of them. But the them doesn't change. Okay, part B is a little bit more involved. What are we gonna do? We'll just read along. So here's the original problem. Square root of 12 minus 2 square root of 75 plus 7 square root of 27. Can we smush those radicals together in their current form? And the answer is no. The only reason we could smush together the previous problem was that it was a radical 7 and another radical 7. They have to be exactly the same for us to smush them together. So it seems like we're out of luck and there isn't anything we can do because 12 is not the same as 75, is not the same as 27. But it turns out we can simplify these radicals, and maybe, just maybe, they'll be combinable at the end. So 12 is not such a nice number under here, but what number goes into that that is a perfect square? You can check your list if you don't have them memorized yet. Perfect square that goes into 12 is 4. So we can rewrite that 12 as 4 times 3. So all we've done is rewritten the 12 as 4 times 3. I'm just going to keep following that one piece. 4 times 3 inside of a radical. Okay, I know that multiplication works nicely in radicals, so I can split that up as a square root of 4 times square root of 3. Yes? And then the square root of 4 is something nice. What is it? It's 2. And so then we get to a 2 square root of 3. And that is what we call simplified. There's nothing else we can do with that 3 in there to make it any smaller. So square root of 12 becomes eventually 2 times the square root of 3. Questions on that piece? Okay, different color now. We'll take a look at this 2 square root of 75. Square root of 75 is not a nice number, but there is a perfect square that goes into 75. Look in your perfect squares list. Find the biggest number you can in the perfect squares column that goes into 75. What is it? is 25. Do other folks see that? So we're just looking down the list. You don't want to find any old random number that goes in. You want a nice number, a perfect square in this case. So 75 is really 25 times 3. So it's still 75, but we've written it differently. And then 25 times 3 under one radical can become two different radicals. Radical 25 times radical 3. See it? And that 2 in the front has just been copied down every time. Square root of 25 is really 5. So that's there. And then we've copied everything else there. And then finally, how can you smush together things here? Multiply the 2 and the 5, because now they're both out in the front. So 2 times 5 becomes 10, radical 3. See it? I'll highlight this 2 radical 3 again, just copied from the previous one. I'm not going to look at the last piece. It's the same idea. You can check it out later if you're interested in. But now, can you combine these final 2 green and blue things? 2 radical 3 minus 10 radical 3? Can we push them together? We can. And what do we get? Negative 8. What? Radical 3. Okay. Yes. Yeah, and so I'll do one different color here. The one that we've ignored is that radical 27. It turns out to become a 21 radical 3. So now we can smush all of them together. 2 of them minus 10 of them, that's the negative 8 of them you guys just said, plus 21 of them, so that's 13 of them, 13 radical 3. So smush as many of them together as are all exactly the same. Lots of radical 3s. So again, this is another kind of like time-consuming process, but this is a really common test or question. So expect to see stuff like this. Okay, so one last thing for the demo. I said it was going to be long, so here's the last piece of today. Let's find the following. Square root of 5 squared. I know we have a shortcut, but our shortcut actually isn't quite valid. So let's do this one without our shortcut. 5 squared is really 25. Square root of 25 is 5. Super. And that was kind of silly to do, wasn't it? Because square root and squared are opposites. So we didn't really need to do 25 to know the answer was just going to be the 5 that we started with.
Why didn't the shortcut work?
The shortcut did work, but it's not going to work in this next one. Okay, so let's do this guy. Square root of, how much is negative 5 squared? Is it negative 25? It's 25 because that square is applying to that negative. So 2 negatives make the positive. And how much is the square root of 25? It's 5. So here's the problem. The problem is that this 5 ended up just being the answer. That was our shortcut. But this negative 5 did not end up being the answer. Agree? Somehow we lost that negative sign. So when we say square root and squared cancel, it's really only a partial truth. They did in the first case, but they didn't quite cancel in the second case. If they did, we would have gotten negative 5 as our answer, not positive 5. Okay, let's take a look at part B. Cube root of 5 cubed. 5 cubed, if you don't know it, it's on your perfect cubed list. How much is 5 cubed? It's 125. And then how much is the cube root of 125? That's 5. So far, so good. Okay, very careful here. Negative 5 cubed. I'm going to write 125, and I'm going to ask you if it's positive or negative. It's negative, right? Because there's 3 negatives multiplied together. And how much is the cube root of negative 125? Is negative 5. Because negative 5 times another negative 5 will give you the negative 125. Okay, so did our shortcut work here? Let's see. Did the 5 end up being the answer in this case? Yes. Did negative 5 end up being the answer in this case? It did. Okay, so there's something complicated going on here. Because sometimes it just works, like in this second row. But in the first row, it only worked for the positive 5, but it didn't work for the negative 5. Yes? Yeah, so what do you think is the Yeah, if we take something to the fourth power, if we had another row of this, then that -5 raised to the fourth would become positive. We would lose that negative because we're raising it to the fourth power, an even power. Yeah, so we're going to have two different rules, whether the exponent is even or odd. If the exponent is odd, then everything is hunky-dory. Whatever number was in there just gets copied. Even if it was negative, it just gets copied. But if that exponent is even, things are more complex. Okay, can you guys tell me something that I can do with the number 5 that keeps it the number 5, and I can do the same thing with the number -5 to turn it into a positive 5? It's a symbol that you have maybe seen in another math class, not in this one. What is it? An I. Oh, I is a good guess. It's not an I here. We will talk about I later this semester. Absolute value is what we're after here. You guys know about absolute value? Yeah, two vertical lines. Yeah, and so something that maybe you guys know. So 5 and -5, absolute value, absolute value. How much is the absolute value of 5? That's just plain 5. Absolute value of -5 is positive 5. So absolute value, if it's positive, it keeps it. If it's negative, it makes it positive. And that's exactly what we're after here, because that power, the even power, is just going to take everything and make it positive no matter what. So our big conclusion is on the next page. It says, if n is odd, then the nth root and the nth power just plain old cancel, and you just take the number that was inside and you copy it outside. So it's just plain a, okay? Don't read the shortcut just yet. If n is even, then the answer isn't plain a. What is it? It's absolute value of a, all right? So if you're odd, you don't have to do anything. The shortcut works. But if you're even, you need to bring in this absolute value. Okay, don't know how useful they are, but this was my way of maybe helping us try to remember. So if n is odd, you don't modify. Okay, so that's not how you spell modify, but that's all right. So don't modify, meaning don't do anything special. Don't change it, just copy the thing that's inside. But if n is even, then absolute value gets its revenge. Even is inside of the word revenge. Like I said, I don't know how useful it will be, but maybe that will be enough to remember, for us to remember how to tackle these. Yes, if it's even, you put in the absolute value. So value takes its revenge. Okay, so then here's our updated thing. I told you a lie before, but now I think we've got the full truth in front of us. So, so if n is odd, then we get to just do our plain division thing. That's what we said earlier today. But if n is even, we do our division thing, but we bring in that absolute value, and that's not something we did. We'll get halves next class. For right now, everything will go in evenly. It's quite possible to get halves. We're just not going to get them today. Okay, so let's take a look at this guy right here. First, we're going to do our old shortcut, and then we're going to update it with this absolute value as necessary. What do I do with the power and the index? Divide. So we get x to the 5. What do I do with the power and the index? Divide, and we get x to the 4. But for one of these, we need to bring in an absolute value symbol. Which one? Which one of these is the one that needs to get the absolute value? Is it? Let's see. So it says here, all right, so keep in mind where the n is. Green is good. This is the thing that dictates. So if you have an even root, that's the one where we got to bring this absolute value business in. It's the even root. Okay, so which one is it? It's that first one. That's the one that needs the absolute value. It's because the index is that 6. The other index is a 9. No problems on that one. Okay, so again, sorry for the long demo. Activities start on the next page. Take your time as you work through them and raise the flag if I can help.